And this first one is 1455. You notice that this delta E is a little bit different. When I take 1455 and subtract off 1314, I get positive 141. So the reaction we did before was negative. It was releasing energy. This one is absorbing energy. Reactions can do one or the other or both. Well, not both at the same time, but you'll see one or the other. If there's any questions so far, you can chime in with your mic or you can type something into the chat. All right, I'll see it. I do want to make sure I'm answering all those as I go along. But for the most part, you should see, hey, okay, I just take the beginning, add that up. I take the ending, I add that up, and I subtract the two. And where do I find all those numbers? They're on that table on the bottom. You'll have access to that table both on your homework and on your quiz. Okay, again, chime in. I do have one more example. I want you to look through this, right? So you want to be looking for what bonds should I be looking for in the beginning. Okay, try to find those numbers before I do. We've got, we're going to highlight red our bonds that are broken. We see the CH, 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 CH. There's 4 of those. There's a C double C. And there are 3 double bonded O's. So where are those numbers on my table? I've got the CH is right here. C double C, right there. Again, don't use 2 of the single bonds. And then an O double O. Those are the only 3 numbers I need for the beginning. But when I do use those, I will put a 4 in front of the CH because there are 4 of those bonds, so it's 413. I will add to that the 614 from the carbon double bond. And then there is the 495 from the O double O, but there are 3 of those. So it's 3 times 495. And when you add this together, remember your order of operations. You do the multiplication first and then add the 3 numbers together. When you do that, you should get a number that I have here. How do you know which order to put the equation in when it's set up like that? Okay, so actually I just picked to put the CH first. You don't have to put the CH first. So the question is, what order do I go in? Can I do the 614 first? Yes, right? As long as I'm multiplying the 4 times the CH. In fact, I'll do the second one backwards and it won't matter because all you're doing is you're flipping the addition. So there's a little bit of math that goes in there. But regardless, even if I switch things around, I should still get 3,751. Even if I do like 614 plus 4 times 413. So math is friendly to us for the science version of it. Now I'm going to go over to the other side. If I didn't answer that question clear, you can ask again. So I've got the C double O's, and then I've got 4 OHs here that I'm forming. Those are formed, so those are going to be subtracted. I'm going to use blue for that one, okay? And I'll flip the order. We'll do the water first, and I'll show you that it should end up being the same thing. My OH I need to find on here, 463, and my C double O is right here, 799. But we're going to do the OH first. So we're going to do 4 times 463. That's from the OH. And then I'm going to add on to that 4 times 799 for the C double O. Oh, and you should notice that's a combustion reaction, right? Because we've got CO2 plus H2O in the products. That total is 5048, but those are subtracted. So it ends up being 3,751 minus 5,048 for a total of negative 1297 kilojoules per mole. So again, that's a reaction that's releasing energy. In fact, it's combustion, right? So it makes sense. Things are on fire. It's really hot. It's letting out a lot of energy, heating its surroundings. But either way, it's just an addition and subtraction problem. That's the homework you're going to have tonight. So if you do have any more questions, you can bug me as you go along. You can always send an email or a text or whatever. I've got lots of info out there. You can find me. So We've got our energy change for the second part. We're going to be looking specifically at some terms in there, and there's some graphs to read. So for our energy change, that's going to be positive if energy increases. It's going to be negative if energy decreases. And mathematically, what that turns out to be is we're going to get that positive number if it's gaining energy and that negative number if it loses energy. And those are attached to these two terms. If it's positive, or if it's negative, that means the reaction is releasing energy. Negative means it's going out, right? It's a net loss. But what that means in terms of what we look at is if a reaction is releasing energy, it's very hot. And we call that exothermic because the energy is going exo, it's going out away from the reaction. We don't look at it from our point of view, we look at it from the reactions, the atom's point of view. And we get that positive gain if the reaction is absorbing heat. If the reaction absorbs things from the surrounding, that's what we feel as cold, right? And we call that endothermic, meaning the reaction, the energy is going into the reaction, making things cold. So I use that red and blue to kind of, match those two. And you should know the difference between those two numbers and be able to talk and use that. Then we also have these graphs. And for these graphs, see if I can get that to actually show up. For those graphs, what we're looking at is energy versus time. And the energy starts at some level. I don't know how high, it doesn't really matter where it goes. It'll be different for each graph you look at. But the reactants are at a set level of energy, right? They have certain bonds in them right now. And what I have to do to those bonds is I have to break them. And do you remember whether breaking bonds will put energy in or release energy out, right? You can always grab a magnet to figure out, right? If you're taking the magnet off, you have to pull. So you have to put energy in. And so what's going to happen to this graph? Well, energy's on the left. It's up and down. Time is to the left and right. So if I go to the left, the energy will go up as I break the bond. So watch the graph. It goes up. There's a little hill in the graph where it goes up. That's where the bonds are broken. And then bonds being formed releases energy, right? So how should the graph continue on? Well, if it's releasing energy, the energy should go down to the right. So you end up with this little hill, okay? And then at the end, you have your products left over in there at a flat line. So it almost looks like a little mini golf course, right? I could have my golf ball right here, and you got the flag of the hole down there, okay? Right? You're gonna have to hit that golf ball if you have your, club here. Okay, that's a croquet mallet, but whatever. You're gonna hit it, you gotta hit it hard enough to break the bonds so that the bonds can form on the way down, right? Otherwise, if you don't hit it hard enough, that ball's just gonna come rolling back at you, and there's no reaction that's gonna happen. So we're gonna use this to identify some properties of each reaction, okay? If you take a look at this, I've got my bonds breaking right here, and bonds breaking right here. That's the positive part of the energy, right? Wow, that's a really bad plus sign. My apologies. And then we have our negative part right here and right here. This is the negative part of the graph. So overall, if it goes up and down more, like what's happened to delta E here? Will it be positive or negative? Well, mathematically, if the negative is bigger, delta E is going to be negative. And here, you see the graph ends up higher than it was before. So the change in energy is positive. I don't have specific numbers for that yet, like I did with the actual bonds we looked at. But overall, I can just look at a graph, and I can say, hey, this first one is exothermic because delta E is negative. It's releasing energy. It has less energy afterward than it had before. And the one on the right is endothermic because it has more energy than it had before. It sucked energy in over time. Because it's all about where that second flat line ends up. Is it higher or is it lower than it was before? Okay, and then I'm just going to attach some numbers to the graph and we're going to actually look at it. We have some terms to look at first. The first term is called activation energy. Activation energy is the amount of energy needed to break a bond at the start of the reaction. If you remember from your beaker app, sometimes you had to light a match to actually get the reaction to happen. It didn't happen enough. It didn't happen if it couldn't get over that hill. And that match was the energy it needed to go over that hill. We call that energy activation energy, EA. That's that first term, right? Activation energy. Here, this graph has a little bit of a higher activation energy, right? It's the height from the first part to the top of the hill. From the first part to the top of the hill. Wow, that was a terrible actual attempt at those lines, but just bring them down a little bit. The total energy is the difference between the reactants and the products. That's delta E. The difference between the reactants, hey, that's better, and the products, right there, that's delta E. You can see that delta E for the first one is negative, it's gone down, and the delta E for the second one is positive, it's gone up. But you're looking for those distances on the graph. And what I'm going to give to you guys is a graph that looks like one of these. And I'm going to say, hey, what's the activation energy? And what's the total energy? So what's EA for this one? Well, that's simple, right? That's from the reactants to the top of that hill, which I've told you is 15 kilojoules. And what's delta E? Well, that's from that first line to the products, which you can see is negative 5 kilojoules, because we're looking at it in the down version, right? We got to add that negative sign there just to keep whether it's losing or gaining energy, because that is a difference. All right, and I might pull some geometry stunt on you. Like, imagine I don't give you that 5, and I just say, hey, so this total is 20. If you remember your geometry and your segment addition, you can just go, okay, well, 20 minus 15 is 5, so that other length must be 5. All right, so don't get like stuck on the geometry curveball. It's just addition and subtraction. You're just looking at a graph. Okay, and specific parts of the graph. Yeah, let's look at one more. I've got an activation energy here of 78, because that's the amount of energy it took to get to the top of the hill. And then the real difference between them is that 57, and this one, this delta E, since it went up, is going to be a positive 57 kilojoules. And again, I might give you two numbers that aren't those two numbers, and you might have to do some segment addition, but no big deal. And then last but not least, I might ask you to draw one of these. So I give you delta E, and I give you activation energy, and I say, hey, draw your graph. Well, you notice how 5 is a lot smaller than 56. So my bump is not all that tall, right? But it releases 56, so it's going to go way down comparatively. It doesn't have to be a perfect graph. It just has to be a general with a flat line, and a hill in the right direction. Okay, one last one. Here it's positive 164, and the activation energy is 320. So the activation energy is a lot, right? There's a big hill in that one. But the delta E is only 164. It's about half of the 320. So I'm going to go about halfway down and draw my flat line. That one's endothermic. That's the positive reaction that you get there. So again, we look at this one. This one's got a negative delta E, so it goes down. And this one's got a positive delta E, so it goes up. And you should know the difference between those two. My screen's backwards, but that's okay. All right. At this point, I'm going to stop the recording.